Hello students, so till now we have discussed about combinational circuits, detail about combinational circuits testing, and today's topic is based on the testing of sequential circuits. तो क्या प्रॉब्लम है टेस्टिंग करने के लिए sequential circuit में टेस्ट जब हम अप्लाई करेंगे, what are the problems that we face in case of sequential circuits? Here it is the classical example of sequential circuit. This is the combinational logic, primary inputs, primary outputs, and a feedback path is connected from output to input through the flip-flops, that is the memory. Okay, memory units you can say. So latches, flip-flops are there. You already studied about the sequential circuits. So in sequential circuits, because of the involvement of these flip-flops, we will bridge the next state and the present state through this particular loop or through this particular feedback. So what is the problem? Flip-flops are internal and inside the circuits. Hence, they are not directly connected to the primary inputs and outputs. You can see from the figure. Flip-flop is internal. It is not connected to the primary input or primary output directly. It is connected with states. So state variables are there in case of flip-flops. ये है difficulty. Next, hence you cannot directly initialize the flip-flops and also you cannot observe the states. ओके क्योंकि डायरेक्टली इनिशियलाइजेशन करने के लिए आपके पास वो पाथ में डायरेक्टली होने भी तो चाहिए, पर दे आर नॉट इन द डायरेक्टली, दे आर नॉट इन द पाथ, you cannot see them directly in the path. So the involvement of flip flops are indirect. So this is why the testing of sequential circuit becomes difficult, because the features of controllability and observability gets diminished. So you would say that if I am going to test the sequential circuit, I have to take care of various things. It is unlike the combinational circuits where we see the direct inputs and direct outputs, and we can apply the fundamentals of various test pattern generation and schemes that we have already studied. But in case of sequential circuit, you have to take care about it. Also, the sequential circuits can have n number of states, as I said already. Testing vectors of sequence are very difficult to design. सो इतनी टेस्टिंग इतने स्टेट्स के बीच में स्विचिंग होती है आपके फ्लिप फ्लॉप्स की, सो इट इज वेरी डिफिकल्ट टू डिजाइन दी testing circuits for sequential circuit. So now hence design for testability circuits are adopted for testing the sequential circuits. So today we are going to cover all the theoretical parameters related with design for testability, and design for testability is specifically for I would say the sequential circuits. एंड ये जो है तीन पार्ट में डिवाइडेड है, मतलब तीन डिफरेंट कैटेगरी है. एडहॉक टेस्टिंग, स्कैन बेस्ड अप्रोचेस, एंड थर्ड इज बिल्ट इन सेल्फ टेस्ट. सो वन बाय वन इसको कवर करेंगे. द कीज टू डिजाइनिंग सर्किट्स दैट आर टेस्टेबल आर कंट्रोलेबिलिटी एंड ऑब्जर्वेबिलिटी. ओके, कंट्रोलेबिलिटी मतलब मीन्स यू कैन कंट्रोल द डिजाइन, you can control the test sequence of the design, and then you can at the same time you can observe them. So observability and controllability must be higher. Restated controllability is the ability to set 1 and reset 0 every node internal to the circuit. Yes, observability is the ability to observe either directly or indirectly the state of any node in the circuit. Good observability and controllability reduce the cost of the manufacturing testing because they allow high fault coverage with relatively few test vectors. Obviously, if you can observe the outputs easily, if you can control the input outputs easily, then obviously the test cost will be decreased, isn't it? And at the same time we take lesser efforts to test or to control or observe the particular circuit. Fault coverage will be higher. So moreover, they can be essential to silicon debug because physically probing internal signals has become so difficult. So there are three types of, I would say the three categories of testing are there under the design for testability. First is ad hoc testing. Ad hoc test techniques, as name suggests, are collection of ideas aimed at reducing the combinational explosion of testing. They are summarized here for historical reasons. They are only useful for small designs where scan, ATPG and BIST are not available. So if scan design is not there, automatic test pattern generation is not there, BIST is not there, then you will say that ad hoc testing can be useful. So what is scan based test technique and what is BIST, we will be seeing later. A complete scan-based testing methodology is recommended for all digital circuits. Having said that, the following are commonly used technique for the ad hoc testing: partitioning larger sequential circuits, adding test points, adding multiplexers, providing for easy state reset. So these are the things that comes under the ad hoc testing. Okay. एक बार फिर से बता देता हूँ, आज की जो क्लास है, आज का ये जो लेक्चर है, इसमें वी आर गोइंग टू सी अबाउट द थ्योरेटिकल पोर्शंस, and then we will move to the individual portions of BIST and scan based technique. Okay, so that you can better understand in this circuit itself, or how we can apply those particular ideas in the circuit so that we can test. A technique classified in this category is the use of the bus in a bus oriented system for test purposes. Each resistor has been more loadable from the bus and capable of being driven onto the bus. Here the internal logic values that exist on a data bus are enabled onto the bus for testing purposes. So we are not going into the major details of ad hoc testing. Ad hoc testing is not very popular, and not it is used for the I would say practical circuits. Okay, so experimentally, practically, scan based design is there, ad hoc testing is there, sorry, ATPG testing is there, then design for testability is there, and then BIST is there. So the scan design strategy for testing has evolved to provide observability and controllability at each register. In design with scan, the registers operate in one of the two modes. In normal mode, they behave as expected. In scan mode, they are connected to form a giant shift register called a scan chain, uh, spanning the whole chip. Idea is clear. So two modes are there: scan mode and normal mode. Normal mode means the circuit behaves normally. Scan mode means it goes into the scanning mode, and a chain of registers are connected in the scanning mode. Okay, so again I am saying I will cover the scan design separately. I will cover the BIST separately in coming lectures. But here it is sufficient for your university point of view. I mean, if you are writing the university examination, it is sufficient. By applying n clock pulses in scan mode, and n bits of the state in the system can be shifted out, and new n bits of state can be shifted in. Shifted out and shifted in, shift registers are there. So in scan mode, n bits of state in the system can be shifted out and new n bits can be shifted in. Therefore, scan mode gives easy observability and controllability. Obviously, because you can see which bits is shifting, which bits is shifting out, which bits are shifting in. So you can easily observe that. Modern scan is based on the use of scan registers as shown in this figure. The scan register is D flip-flop preceded by a multiplexer. When the scan signal is deasserted, the register behaves as a conventional register, storing data on the D input. When scan is asserted, the data is loaded from the SI pin, which is connected to the shift register, fashion to previous register Q output in the scan chain. Simple logic is there. The logic is simple. We can understand from here. So these are the registers. These are the registers, and this is the scan in, and this is the scan out. So one by one, the bits are inserted here: 1 1 1 0 or 0 1, whatever may be the test pattern, and then it is shifted from here. You can say from here it is shifted to here, from here it is shifted to here, and so on. And then finally scan out. So scan out means nothing but the you are checking what scanning has been done, whether the output is correct or not, whether the testing has been completed or not. So scan in is nothing but the pattern that you are inserting, and scan out is nothing but the result that you are observing. Okay, so from the input to from the circuit to load the scan chain, scan is asserted and clock is pulsed 8 times to load and first two ranks of 4-bit register with data. ये जैसा मैंने आपको बताया, ठीक है. Scan is deasserted and clock is asserted for one cycle to repeat to operate the circuit normally and predefined inputs. Scan is then reasserted and clock asserted 8 times to read the stored data out. Okay, so 8 times you are saying the scan is reasserted, and then it is stored and data out, I mean scan out is there to observe the results. At the same time, a new register contents can be shifted in for next tests, and testing proceeds in this manner of serially clocking the data out to the scan register to the right point in the circuit, running a single system clock cycle and serially clocking the data out for observation. In this scheme, every point to the combinational block can be controlled and every output can be observed. In addition, running a random pattern of ones and zeros through the scan chain can test the chain itself. So this is how we can do this. Test generation for this type of test architecture can be highly automated. ATPG techniques can be used for combinational blocks, and as mentioned, the scan chain is easily tested. The primary disadvantage in this area and delay impact of the extra multiplexer in the scan design. So designers are in widespread agreement that this cost is more than offset by the savings in the debug time and production test cost. Okay, now the parallel scan. You can imagine the serial scan chains can become quite long. Obviously, you are shifting the bits serial by one by one, one by one, one by one. Similarly, in case of the scan out, you are observing the data serially also, because serial in serial out is there. So, what is the parallel scan? So in case of a fairly simple data is to split the chains into smaller segments. This can be done on a module by module basis on a completed automatically to some specific scan length. Extending this to the limits yield an extension to serial scan called the random access scan, or also known as the parallel scan. Okay, to some extent this is similar to that used inside the FPGA to load and read the control R. So the basic idea is shown over here in the figure. Okay, so two register sections are there. Each register receives a column and row access signal along with a row data line. A global write signal is there that is connected to all the registers. So a global row data, this is row, this is data, these are the rows, and this is n plus 1 means whatever n is there. If you say that three rows are there, then 3 plus 1 4. So this is how it is defined, and this is the customized register. This is the logic we are using inside it, and it is nothing but the multiplexer connected with the D flip flop. This is the multiplexer, 2:1 multiplexer connected with the D flip flop. Okay, scan bed design. This is very important. This figure is very important. This flip flop is controlled by the output of 2:1 multiplexer, and write data low and column inputs are there. Row input, column input, and similarly write and data inputs are there. Okay, see the combinational logic is shown to the right of the register. 4 registers implemented logic required at the transistor level can reduce the overhead of each register. Yes, so this is the thing that we studied. Now scannable register design. This is the scannable register design I already covered. 2:1 multiplexer should be there preceding the D flip flop. Okay, so 2:1 multiplexer preceding the D flip flop shown over here. So different diagrams are shown for the scannable flip flops, and the idea is nothing but only the idea, basic idea is same for all the testing circuits. The first input is the first circuit is multiplexer followed by the D flip flop. The combination of multiplexer and 2:1 multiplexer followed by the D flip flop is the basic of the scan based design techniques. Okay, so built-in self-test technique. Self-test and built-in test techniques, as their names suggest, rely on augmenting circuits to allow them to perform operations upon themselves that prove correct operations. These techniques add area to the chip for the test logic but reduce the test time required and thus can lower the overall system cost. Let me explain built-in self-test techniques, because I have published many papers on built-in self-test techniques. So the basic idea of built-in self-test technique relies upon involving the entire test circuit inside the chip itself. Suppose I am preparing a phase log loop of PLL. So why would I not embed the testing circuit inside that particular I would say the chip. So if this happens, then though the area will be higher because you are inserting the testing circuit inside that original circuit or original chip, but then you need not to apply the testing pattern externally, and this will yield the better test results. The fault coverage will be higher, and in this manner you can say that a lot of time will be saved. Okay, so let us see some built-in self-test designs here. One method of testing a module of use signature analysis or cyclic redundancy checking. This involves using a pseudo-random sequence generator. Pseudo-random sequence generator can also be, generated by uh, the combination of registers, I would say, that is known as uh, linear feedback shift register, LFSR. Here, yes, here it is there. So a PRSG, pseudo random sequence generator of length n is constructed from a linear feedback shift register, as I said, LFSR, which in turn is made up of n flip flops connected in serial fashion, like this, connected in serial fashion, and XORing will be there at the output. Okay, so an n bit LFSR will cycle through 2 to the power n minus 1 state before repeating the sequence. Yes, n is nothing but the number of, you know, uh, I would say the flip flops you are connecting. So LFSR are discussed further in section. You can go and see the section 11.5.4. This is not for LFSR characteristics. They are described by a characteristic polynomial indicating which bits are fed back. A complete feedback shift register shown in figure 15.19. This is a feedback shift register. If flops states are there, then again you are coming here, again you are applying here, then again you are coming. Continuously you will be, seeing the feedback, and then this is why it is known as feedback shift register. Okay, so an n-bit LFSR is converted to an n-bit CFSR. CFSR is a complete feedback register by adding n-1 input NOR gate connected to all but the last bit. Okay, when in state 0, let's say 0 1, the next state is 0, say 0 0. When the state 0 0 0, the next state would be 1 0 0 0, because the next cycle last is 0, then you are adding as 1, then 1 is shifted to 0. So here I would say like this. So 1 is there, next state 1 shifted here, next state 1 shifted here, next state 1 shifted here, then here, and so on. Otherwise the sequence is the same. Alternatively, the bottom n bits of n plus 1 bit LFSR can be used to cycle through all zeros and state without the delay of the NOR gate. Okay, so a signature analyzer receives successive outputs of a combinational logic block and produces a syndrome that is a function of these outputs. The syndrome is reset to 0 and then XORed with the output on each cycle. The syndrome is swizzled each cycle so that a fault in one bit is unlikely to cancel itself out. As a test of a test sequence, the LFSR contains the syndrome that is function of all previous outputs. This can be compared with the correct syndrome to determine whether the combinational good or bad is there or not. If the syndrome contains enough bits, it is improbable that a defective circuit will produce the correct syndrome. So built-in self-test, the combination of signature analysis and the scan technique creates a structure known as built-in self-test. Okay, so BILBO, the built-in logic block observation. It is given by the phenomenon, the 3-bit in 1979. The 3-bit BIST register shown in figure 15.20 is a scannable resettable register that can serve as a pattern generator and signature analyzer. It specifies the mode of operation. Let us see the diagram. This is the diagram. This is the built-in self-test technique. 3-bit register is there used in a system. So we are applying the pseudo-random, signature, sequence generator here at the input. logic cloud that we are going to test, and then we have to analyze whatever output we are getting at this instant, at this particular node. Signature analysis will be there. Signature analysis is nothing but observing the outputs, whether we have obtained the correct result or not. I mean, the circuit is faulty or not faulty or fault free. So this is nothing but the signature analysis. Now here you are saying, you are seeing here the scan mode. So both, if C0 and C1 both are 0, if both are 0, then scan mode will be there. If C1 is 0 and C0 is 1, if C0 is 1, then we are enabling the testing process. If C1 is 1 and C0 is 0, then reset operation is there. And in case of the normal operation, both the outputs will be 1. Both the inputs will be 1. So let us start from the normal operation. Normal operation means C0 is 1 and C1 is also 1. If both the inputs are 1, then AND gate input is 1. So if AND gate input is 1, whatever may be logic you are providing here, that will be forwarded here. Because you are knowing that if one input is AND gate, then it acts as a non-controllable input. If both the inputs are, I mean, if the input is 1, then the logic is non-controllable for this particular uh, gate. So whatever logic that is coming over here, that will be forwarded here. So this is the normal mode. Reset mode. Reset mode, C1 is 1. C1 is 1. So C1 is 1. C1 is connected to here. Okay. C1 is connected to here, and if C1 is connected to here, then you can say that you will be seeing the reset pattern. Here you can see the reset pattern. Here you can see the reset pattern. Here you can see the reset pattern. When C0 is 1, when C0 is 1, C0 is connected here. Now when C0 is 1, one of the input is 1, then you can apply the testing sequence here from D0, then D1. These are the data inputs, D0, D1 and D2. And then similarly, you can observe the output from here. This is how the testing process happens. Let me explain it in the detailed manner by providing you the theoretical explanation. In the reset mode, all the flip-flops are synchronously initialized to 0. Okay. In the normal mode, the flip-flops behave normally with their D inputs and Q outputs. In scan mode, the flip-flops are configured as a 3-bit shift register between SI serial in and serial out. Note that there is an inversion logic at each stage. In test mode, the register behaves as pseudo-random sequence generator or sequencer analyzer. If all the D inputs are held low, the Q outputs loop through a pseudo-random test bit sequence, which can serve as the input to the combination logic. If the D inputs are taken from the combination logic output, they are swizzled with the existing state to produce the syndrome. In summary, BIST is performed by first resetting the syndrome in the output register. Then both registers are placed in the test mode to produce the pseudo-random inputs and calculate the syndrome. Finally, the syndrome is shifted out through the scan chain. Okay, so this is how you can understand this. So in scan mode, both are 0. In scan mode, both are 0. This is 0. This is, if both are 0, whatever may be the input towards this, I mean output of this AND gate will always be 0. Okay, so this will always be 0, and you can say that whatever data you are providing for scanning, that will be shifted from here to here to here to here, and then you can say this is the output is again taken to the XOR gate, and here the n-1 output is taken here, XORing will be there, and then again it is applied to the 2:1 multiplexer, and accordingly 1 or 0 is again supplied here. The logic of 1 or 0 is again supplied. SI means the serial in data, and this is the serial out data. Okay, so this is how built-in self-test techniques are designed. Memory BIST is also there on many chips. Memories account for the majority of the transistors. A robust testing methodology must be applied to provide reliable parts. In a typical memory based scheme, multiplexer are placed on the address, data and control inputs for the memory to allow direct access during test. So various other test strategies are also there, but they are not of our use. We will close the topic here of today's lecture. So these are the different techniques which comes under the category of design for testability. And again, I am saying that I will cover the scan based design and built-in self-test technique in a separate lecture so that you can understand in the better manner. Because just understanding theory is not sufficient unless and until if you apply it is on the circuit. Okay, so in coming couple of lectures I will cover it. Thank you for listening and watching to this particular lecture.